questions before we get started. And so you can continue to turn stuff in up at the front. And then I do have some homeworks that I'll try to get back to you. And I actually did try to give you feedback as well, so I don't normally do that, but especially for the sig figs, I at least try to glance over your homework. So I'll try to do that, again, as much as I'm physically capable of. Oops. All right, so let's finish or continue our tour of the periodic table. So again, both looking at electron configuration, but then also trying to piece that together with, well, what the heck are we really seeing? What information are we getting from this? So let's do a little warm up here. So let's try oxygen. So let's just write the electron configuration for oxygen. So I'll give people a few minutes to attempt that. So what do we get for the electron configuration? So what should we start with? Someone can start us off. So where do we start? 1s. So 1s, but then how many can fit in the s orbital? 2. So 1s, 2. And again, right, we just follow along in order. So what comes next? So 2s, 2, perfect. So we're just going along, filling all our elements in until we get to oxygen. And then what's the last part? So 2p4. Excellent. And again, let's look at what information this is telling us. And so our outermost shell, again, these are our valence electrons. And so we can say oxygen has 6 valence electrons. So anything other than the valence electrons are just called your core electrons. So these usually do not participate in bonding since those would be deep. So those would be localized on the atom itself versus these bonding orbitals. And so that's something else that you could put on the periodic table. So I'm going to make a new copy. And again, if you need extra copies, I can make more. But the numbers are here to kind of help you. But again, if you want to write this down, So, right, these little numbers also correspond to their valence electrons. So we were looking at oxygen. So notice it's under group 6. So again, that's 6 valence electrons. That means everything in this same column, right, in that same family, they all have 6 valence electrons, so they're going to have similar reactivities. So going back and just filling them in for all of them, right, this has 1 valence electron, 2 valence electrons. So again, notice, right, you have this 1, 2. We'll skip the transition metals because they get funny. And then 3 valence electrons, 4 valence electrons, 5, 6, 7, and of course, right, 8, with obviously the exception of helium, where it has 2. So again, just noticing that pattern. And so you'll also start to see, so what do you think the Lewis dot structure would look like? So try to draw it out, and then I'll also fill in, so I'm going to rewrite this in a different perspective. So what does our oxygen Lewis dot structure look like? Any guesses? And I gave a trick. What was the trick to try to translate it? Do y'all remember? So it was kind of rushed. And so again, right, these are valence electrons. And so there's 4 orbitals, right, 3 p's, 1 s. So I said we could translate them to our sides here. And so right, we go. And so there's a proper way to do it. So I'm sure you guys learned in like elementary, or not elementary school, but like high school or middle school. Did you ever do like the candy rule? And they're like, put an electron in each side or whatever. Do y'all know what I'm talking about? No? Well, so basically what the candy rule was trying to do is you want to fill each electron, again, with the lowest energy orbital first. And so usually what happens in people's like elementary understanding of this is usually they say like put an electron on each side. So you're like 1, 2, 3, 4, 5, 6. And that does give you the right answer in this case, but I would say it's not really accurate, and we want to get a deeper understanding now. And so again, that's why I say let's translate our valence electrons then as each one of those 4 sides. And so again, that makes one of the sides, it doesn't matter which is which, it's 3D, so you can orient it. But let's just call this a 2s essentially. Then the remaining ones will be our 2p's. So truly with the candy rule, I guess you're not familiar with it, but again, we want to fill up our lowest energy level first. So we have our 2s, so that's why we put 2 dots on one side first. Again, this probably goes against what textbooks will say, but textbooks aren't necessarily giving you a good understanding of the MOs. And then, well, with these, so these p orbitals, why I drew them in a straight line here is we have a term called degenerate. So we would say these are degenerate, which means they are the same energy level. So basically, right, it costs the same to put them in each one. And then why we do this little candy rule of putting 1 in each orbital is because we do pay a price for pairing. So, right, these 2 that are occupying the same suborbital, right, there is a price. So you can say that, right, energy price to pair. And so that's where the candy rule comes in from. So we want to fill in these degenerate orbitals first, so 1 in each p. And so then I'll go 1, 2, 3, and then now we can double up, so giving us, again, our traditional picture. So you don't have to write it right with these 2 p's and the 2s on the side. So it's totally appropriate to just write that, right? That's just your final answer. But I want you to see this, so when you see this written out, right, it translates effectively, and you're not feeling like you're re-deriving everything. And then another note, so again, right, they all follow a pattern. Well, if all these have 6 valence electrons, right, everything in this row is going to have the same Lewis dot structure. So, right, that also goes back to their similar reactivities. So all group 6 looks like this. So we can go crazy, right? Sulfur, selenium. So we know them all just based off of oxygen. And so not to get too excited, but now we're going to start seeing also all the information that's packed into this little Lewis dot structure. Again, very unassuming, but this is giving us a hint to the geometry. And again, we're getting there, but I just want you to start developing this. So, right, these lone pairs, those occupy space. Okay, so they're taking up space. Then we have these little lone electrons. Well, what is that telling us? Well, that's telling us that this wants to make 2 bonds, at least in general. Wants to make. And then we could go crazy coming up with all the different analogs of group 6 that look like this. And of course, right, water is our classic example. Sulfur dihydride would be the same. Selenium, dichloride. This would be rare, but right. So again, you can knock yourself out, and then this is telling us the geometry, which again we'll get to, but you're kind of getting a hint at all the information that's packed in just a periodic table. That's why it's so powerful, is that everything repeats, right? All these things have similar reactivities and make structures. That's how we know what they look like, just based off of everything else. All right, so back to filling in our electron configuration. So again, just keep asking questions. And so we'll look at, so we have neon here, so I'll write neon out just so we're all on the same page. So we have neon, and we could write it abbreviated, right, starting with helium. So helium, 2s2, 2p6. I'll write it the other way as well. So then now that brings us to a completed, right, second energy level. And so now here's again the hint of our octet rule. So here's 8 electrons. And so again, that's another hint, is they want their valence shell to be fully occupied, at least for the most part. That's where you get interesting reactivities if a compound does only have 6 electrons and wants more. And chemists exploit those properties. And so now let's march on. So we go to sodium. So now we're back at 1 valence electron. And so sodium, I'll write in our new abbreviated electron configuration. So starting with neon. And now we're at 3s1. And again, Lewis dot structure for sodium would look like that. All group 1s look the same. Again, doesn't matter where the dot goes. So lithium, potassium, sodium. So again, all showing 1 valence electron. So that goes back to their NS1 ending. So now we're just starting, right, our third energy level. And so we go back to maybe middle school or high school, what you learned with these basic energy levels. So now they have 18. And well, what does that mean? Let's translate that, though, to actual orbitals. And so now once we go to the third energy level, we can have d orbitals. So third principal energy level. And so, right, we still have our s in there. So we have our 3s. We'll have our 3p's, right, with our 3p orbitals. And then in the third energy level, that's where we can have what are called d orbitals. And I guess let's at least look at a picture before I start drawing them out. So d orbitals, I might still draw them out to show you, but it's better to show a picture. And so what you want to take away, there are 5 d orbitals, and so each one of those suborbitals holds 2 electrons. And so let's look at the periodic table. And so it'll take us a minute to get there. So the 3D actually starts over here on scandium. So first we're going to fill up 3s, we're going to go 3p, and again we'll walk through this. Then what's weird is the 4s energy level is actually a little lower than the 3D, but what you'll find is they're pretty close, and this is where the transition metals start to get funny, because then electrons kind of go back and forth between the S and the D, kind of depending on what's most energetically favorable. But here starts the 3D. And so you might want to highlight that. So this is my whole D block now. And so again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 across. So that corresponds to, right, our 5D orbitals. And we could put a note somewhere. So 5D orbitals. And again, 2 electrons in each one. So that's where that 10 comes from. All right, so let's do the electron configuration of chlorine. So again, fill it up in order. So we have 1s, 2s, 2p, 3s, 3p. So give me the electron configuration for chlorine, and then we'll keep practicing. All right, let's hear it for chlorine. What did you get for the electron configuration? You can give it to me either the full shebang, or you could start abbreviated at neon. Yeah.
So I did neon, 3s2, and then 3p5.
Perfect. And so that looks good. So once again, right, let's just identify for clarity. So we have our valence electrons. Oh, it's 7. Let's go back to our periodic table. And yes, we said that was 7 here, so that all makes sense. And we can write our Lewis dot structure, again for clarity. So I would fill up our s orbital first. It doesn't matter which one you call s. So 1, 2, and then 3, 4, 5, 6, 7. And so now we get our Lewis dot structure. And again, we can start piecing together some information. So we have one little random electron here. So this is telling us, right, it wants one bond at least. And so, of course, right, we'll later find they can do funky stuff, but this is at least a good starting point. It's like, yes, it's missing one, so it's at least probably going to make one bond. And this kind of hints as to why they are diatomics, but we haven't quite gotten the full picture, so you need the full MO diagram to fully understand it, but it's at least kind of giving us a hint, right? We got this weird, just little lone electron, and so that's probably why, right, chlorine's going to want to bond to itself, just like the other diatomics. Questions so far? Questions? So let's try a trickier one. So let's see how vanadium goes. So take a minute or so and look at vanadium. So so what do we get for vanadium?
The first bracket is like argon, and then 4s2,
Yep.
and then 3d3. I'm not for sure of that.
Yeah, that looks great. All right, so did everybody get this? So this was good. So again, we can go back to our previous noble gas, right? Start with this. You could have done the whole shebang though, right? 1s2, 2s2, 2p6, 3s2, 3p6, right? That brings us to argon. So if you wrote all that out, that's fine. I'll accept that. And then starting with argon, so we just keep filling up. So 4s2, and then 3d3, exactly. And so for the transition metals, we don't generally do Lewis dot structures, at least not in the traditional sense. So I'm not going to try to draw one out. That would just not really serve a purpose. But now let's look at chromium. So fill in what you think would be the electron configuration for chromium. And we'll go over some issues. So what do we get for chromium? Anyone want to go for chromium?
Would it be, hang on.
What do we think?
So start with the brackets and argon again, and then 4s2 and 3d4.
So this is correct, right, by what we would expect. And I'm going to put correct answer and kind of what is expected. But now I'm going to introduce a little caveat. So again, this would be totally correct if you gave it to me on an exam. But let's say you were checking your work and you're looking at this P table and you look at chromium. And so what's the problem? What do you notice?
It says 3d5.
So it has 3d5 exactly, and oops, there's only one in the 4s. And so I'm not expecting you to remember or know all these exceptions, but I want you to be aware of when they occur, and then I would take both answers. Like if you think it's an exception and you write it that way, I will take it. If you just write it filling it normally, I will also take it. And we can kind of see why. And again, this goes back to how close the 4s and the 3d are. And so this, right, if we write out kind of in our other diagram, so 4s, 3d, and again, they're very close in energy. And so that's the other thing that happens as you go along. So the biggest gap in energy is from the 1s to the 2s. Then each subsequent energy level difference gets smaller and smaller and smaller. So things get weirder and electrons can fly around in different orbitals. And so we fill up kind of what we expect. So 1, 2, and then 1, 2, 3, 4. So again, right, this looks okay. But if you remember, right, we have to pay a price for energy pairing. And so it must just be more energetically favorable to move them around. So again, this energy gap is so small that this is more favorable just to throw it into the D instead of having to pair those two electrons. And so again, this is our actual. And so I would not expect you to write that on an exam, but I want you to at least be aware of it. Or the other thing that I might take on the exam is I might say, like, this is the expected electron configuration, but, you know, this is the actual, kind of explain why. And then you would just say something, right, the 3D and the 4S are so close in energy that it's more favorable to not have that one paired. And so if you play around, right, on the periodic table, you can get a sense of, you know, when it follows the pattern and when it doesn't. So manganese, adding one more electron, right, now it goes back to that 4s being filled in. So that's what we expect. Iron, look, it's, you know, perfectly normal what you expect. Cobalt, nickel, and then copper, you get that oddity again where it throws in all the electrons to the D and then just has a 1s. But then that kind of explains why copper tends to be in the 1+ oxidation state. So same thing with zinc. It tends to be 2+ because those electrons are actually coming from the 4s. So a little confusing. So again, that's kind of why we ignore the transition metals and we kind of talk about them, but not. But things get interesting with the d orbitals. And in truth, right, the d orbitals don't just stay like this. So again, this is when they are degenerate. But as an atom goes and makes molecules, it takes different geometries, and that throws these d orbitals into different energy levels. But that's kind of more advanced. But that's at least showing you why things are weird. So I don't want to just be like, oh, the d orbitals are weird and then move on with life. It's like I at least want you to have an appreciation. There's 5 of them. They move around. They're very close to the 4s, so everything kind of shifts around depending on geometry. But as long as you can just fill it in how I expect it, you know, how you expect it with the periodic table, that's perfectly fine. Okay, everybody still with me? And so let's just continue filling in our periodic table. So we go 3D, but now we're back to 4P here. And so I would write that to remind yourself. And then so finishing out 4P, then that brings us to 5S, then 4D, and then so 5P again. And so see if you can write the electron configuration for tin then. So try tin, and then we'll go over it. Are you ready for 10? So what do we get for 10? Yeah.
So in brackets, krypton, and then 5s2, 4d10, and then 5p2.
That sounds excellent. Is that what everybody got? And so this also starts to get a little odd. So once we get over on this side, right, of course we have all those d electrons, but if it's in the p block over here, we generally kind of ignore them. And so again, right, we just consider these ones to be our valence electron. And so that falls in line with, again, our big pattern here. So I'll go back to the other periodic table with our 4 valence electrons. And so we should at least, oh, and then don't forget to double check yourself. So again, oh, let me pull out my calculator. So you can always write add to double check yourself. So we started with krypton, which I can't read. What did you say? 36. And then plus 2. plus 10, right, just adding our little superscripts, so adding in our electrons, oops. And so that's 50, and then that should match up right with 10, so 50. And again, this is for the neutral, right? So the number of electrons is the same as our atomic number. So just keep that in mind as well, right? You're adding all of this up for the neutral, so if you have a charged species, your electron configuration could change. All right, so let's continue finishing this. So we have 5p, so then we finish this out. 6s. Do we have questions or? So let's finish up. So we're at 4s, and then this is where things can get funny, and you have to look at your periodic table, and then there are going to be more discrepancies. And so I disagree with this periodic table. So first of all, let's figure out what comes next. So we have our f orbitals. So let's talk about our f orbitals. So we said D, there were 5 of them. And so now on our 4th energy level, we have S, P, D, and now F orbitals are invoked. And I usually never draw them because they look crazy. I can kind of draw the D's. I'm not the greatest artist, but the F orbitals are pretty tricky. I'll get a picture. And so there are 7 of them. So you can at least appreciate how funky they look. So that's why I'm not going to attempt to draw them. But, so F orbitals. So there are 7, 1, 2, 3, 4, 5, 6, 7. And of course, each holds 2 again. So how many total electrons are in our F block across? So 14. And so right away, we're going to notice a problem now. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And so this is where things get awkward. And so it depends where your periodic table has stuck the lanthanides and actinides. So personally, I would put lanthanum here. And so, right, lanthanum is going to be your 5D1. And that matches with here. So notice, right, I don't understand their coloration because I disagree with their coloring based upon the electron configuration. So notice they put lutetium and lawrencium as D block, but I wouldn't say that. I would put lanthanum and actinium as D block, and lutetium and lawrencium are ending your F block. But again, you could see differences. So this is where you get a little bit of differences in electron configuration. Yeah, ironically, they put it in the 5D. So then cerium, if we move over one more, so now, right, we went 57 to 58, and so that's where the 4F1 gets invoked. So on your periodic table, right, I would put lanthanum here, actinium can go here as 6D1, and then cerium starts 4F, and then that means thorium is 5F. And so let's practice one. So let's try europium. So see if you can write the electron configuration for europium. And so you might have to do a little tracing back what your last noble gas was. are we ready to go over europium?
Should it, in the bracket it be xenon?
So, ooh, oh, wait. Yeah, that's right, sorry.
And then 6s2 and 4f6.
And is anything missing? Because you did 62, but then what about your 5D? Because 1, 2, 3, 4, 5, 6. And so this is where things get weird. So I think we skipped 5D1, right? And so that's why it's always good to double check. So let's double check. So xenon. Well, it probably should have been written, if we're going in order, right? 6s2, 5d, 1, 4f6, right? So we'll double check. So 54 plus 2 plus 1 plus 6. So that gives us 63. So that matches with europium.
Why is it xenon and not radon? And then why do you have 5D1 instead of just old D?
So this is where things get weird. So that's why I put lanthanum starts 5D1, right? But then after that, it fills up all the F block before you go back to hafnium of 5D2. And then, yeah, radon, so that's where I had to check myself with the numbers. Because, right, we're looking at 63, so we can't start with radon because it's 86. So we have to start with, like, the lower noble gas, right, to build up. So that's why, so I'm looking at 63, so that's why we had to pick 54 for xenon. And so now let's do tungsten then to give us practice. So yeah, these get weird because you don't want to forget about your 5D1. And so I will say this could be an alternate answer that's not great, but I would accept it. So if you have 6s, oh, I don't know why I wrote my s, dyslexic here. So 6s2, 4f7, that's not ideal because we kind of skipped over lanthanum, but it wouldn't be wrong, right? Does that make sense? So we still have the right number of total electrons. We're still kind of filling it up in order. So we stuck lanthanum in our F block. We could have gotten that. So I'll say, okay, answer. It's just not ideal. So I'll give you a few more minutes for tungsten.
You have to count it.
Okay, are we ready for tungsten? So that, there's some flexibility, so I'm not gonna be like upset whether you swap them. So you probably wanna do the F and then the D, but. So what noble gas should we start with? What did you say? So xenon, and then what happens after xenon? So xenon, what happens? So 6s2, right? So just starting from xenon, so 6s2. So again, put these labels. And then what happens after 6s2? So 4f14. And what's next?
5D4.
5d. And then, yeah, 1, 2, 3, 4. So that looks good there. Did you have something different? And then we can check ourselves. And so looking at our P table here, and so that looks good, right? Everything kind of falls as expected. There wasn't anything weird there. Although, honestly, I'm surprised the S orbital wasn't thrown into the D, but again, always oddities. All right, how are we feeling? I already heard somebody hating chemistry. It's pretty expected. So just hang with the course, yeah.
So for the 57 to 71, that chunk where it moves down, that's 5D. Does it continue to the right, like 71, like 72, 73? Is that also
Yes.
5D?
Yeah, so this goes back to D. So lanthanum starts 5D1, right? And this is where it's weird. So you're at lanthanum, which is 57, and then 58 starts 4F1, and then you fill in all the F block. So right, lutetium is 4F14, and then 71, 72 brings us back to hafnium, so now that's 5D2. Is that starting to make sense? So please don't get discouraged. I know chemistry has a bad reputation. I learned that teaching the summer session, right? We are here, 100-level class, so just keep asking questions, keep hanging with it. Give yourselves props for doing chemistry, doing the math. Like, just keep at it. I know people don't like chemistry. That's what I hear 90% of the time. All right, we will stop here. So we'll take our 10-minute break, and then we'll do our quiz. So it's going to be over last week's material, so sig figs and all that stuff. And then, of course, afterwards, ask questions. I'm here to help. So I will stop this.